Hi everybody, welcome back to the Introduction to Equilibrium Systems. So this portion is going to describe the mathematical context of it. Because we said we can't use a stoichiometry mole ratio to calculate concentrations, we have to use another technique. So in part A, we examined the theory behind what an equilibrium is. Be sure to watch that before we begin this. And we're going to use this reaction here. Nitrogen plus hydrogen produces ammonia. Now, this is known as the Haber-Bosch process, and it was one of the most important reactions because it helped to establish a scalable reaction, which means it can be done at large scales to produce a lot of product for one of the raw materials for fertilizers, because nitrogen is what plants require, and it's provided in the form of ammonia. So, what we're going to look to do here is, in terms of stoichiometry, because this arrow here means not all of the, because this arrow here is double-headed, it means not all of the reactants turned into products. So there's some left over, and we just have to figure out how much of that it is now. Now, the one thing that does apply is that the change is related. That's key. All right, so just like we said, for every 1 mole of nitrogen that's lost, we gain 2 moles of ammonia. For every 3 moles of hydrogen lost, we gain 2 moles of ammonia. So the amount they change by is related, and that is stoichiometric, and it's based on the mole ratio. But the actual numbers are not. So we use this technique called an ice table, and this is key. I'm going to put a star beside it for the entire unit, so we need to focus on this. What they do is help us keep track of changing concentrations, right? And we can use it to determine the concentration of a substance at equilibrium, right? So when the concentration levels off again, if we just draw a quick little sketch, again, equilibrium is when the reactant concentration and the product concentration stop changing, but it's dynamic. Remember that it doesn't mean that nothing's happening, we just can't see it because it's equal and opposite. We can also keep track of the change in the concentration that occurs. So it's important to note here that we'll be doing everything in moles per liter. You could also do it in moles. Okay, but we don't use grams in this case because the changes are in moles, and we're assuming that because everything is in the same reaction, they all have the same volume. So we'll be working with gases and aqueous substances, and we'll go forward from there. So there are 3 parts to an ice table. The initial concentration, this was what was present before the reaction begins, and the product concentrations are, for the most part, 0. Okay, there are exceptions we'll look at later on. We're going to look at the change in concentration. So reactants will decrease by their factor x, and their factor is their coefficient, and products will increase, so we'll see positive x beside a product. And then finally, when we take the initial concentration and add the change to it, we'll get the equilibrium concentration. Okay, now when you add a negative value, it'll look like subtraction. So these are the properties of an ice table. This is just an organizational technique. Okay, an ice table doesn't exist in nature. Right, and initial change in equilibrium is what they represent. So let's look at one with an example. And I'll go to a larger screen for this. So hydrogen fluoride gas is formed by combining hydrogen gas and fluorine gas, and we're given the concentrations of each, their equilibrium concentration, and we're asked to determine the concentration of the others. So it's very important to begin that we start off with what the values actually are. So notice how we wrote the reaction out here, right? And then we put a table around it. And I'm going to just separate off every section of this so that each substance has its own cell. Okay, now this is a very formal table. You can just use the inner lines if you'd like, but this is how it begins. So let's look at our initial concentrations. There is the word initially for us. 2 moles per liter of each reactant gas. So we'll say 2.0 and 2.0. And because we're working on concentration, I'm just going to use the capital M here. There is no product because the reaction hasn't started initially, so there's nothing there. Then we're told, and I'll highlight this in a different color, there's 0.48 moles of fluorine gas at equilibrium. 0.48 moles. Then we're asked to determine the concentrations of the other two systems. So this is the information that we have. So it's fairly straightforward to work with. There's no mole ratios other than identifying a balanced reaction. And in this case, it's already balanced. We have 1, 1, and 2. And we'll add the ones there so we can see. So to begin, remember that the change is the addition or subtraction of some material. We lose reactants and we gain products. So we'll put minus signs for the reactants and plus signs for the products. Now the change, they all change by some amount x, and it's related by their coefficients. So we put their coefficients in front of them, and that tells us how they'll change. So what that means is for every 1 part of hydrogen lost, we'll gain 2 parts of hydrogen fluoride. Now for the equilibrium concentration, we'll say that we add these two together. So this is the first 2 rows added together. 2.0 take away 1x. Right. For this row here, we already have a number, so we'll leave that there, and we'll say 0 plus 2x in this case. So that's how the ICE table works. These numbers here come from the coefficients, and we're given data about the rest. So to find this here, to solve for this, we need a clue about the data. And what we're told is that 2 minus 1x is equal to 0.48. That's for the, actually, let's write these in order. So we're told that 2 minus 1x is equal to the equilibrium concentration of hydrogen. 2 minus 1x is equal to 0.48 moles in this case, which is the equilibrium concentration of fluorine. And then we're told 0 plus 2x, we don't know what the value is, but it's equal to the concentration of hydrogen fluoride at equilibrium. So if we look there, we can solve this statement here. And once we know what x is, that's the value for all of the changes. So we can solve for here. So we'll solve x, and we're going to use a complete column. Okay. So in this case, and we'll just simplify it, we'll add the significant digits back after. 2 minus 1x is equal to 0.48. If we isolate this, we'll get 2, take away that, is equal to x. And we'll say 1.52 moles per liter is equal to x. Now, this is not a concentration. This is what the change in concentration is described by. So we'll say that this gets subbed in. And that allows us to find the equilibrium concentrations. And again, that's just my abbreviation for equilibrium. And concentration is the square brackets. So now let's sub that back in. Right, so in our first case, right, we said 2 minus 1x equals the concentration of hydrogen. So we'll say 2 minus 1.52 equals that. And if we solve, we'll find that it equals 0.48 moles per liter of hydrogen gas. Okay, and just to go back down here to solve the second one for hydrogen fluoride, I just wrote a little bit too big here. 2x, it's 0 plus 2x, which we can just cancel out, is equal to that concentration. Therefore, x is equal to 2. So 2 times 1.52 equals that concentration. And I'm making this very formal. You can probably look at the expression and evaluate it without all of this math, but just to be safe, I'm going to show it all here. So 3.04 moles per liter equals the concentration of hydrogen fluoride. Okay, and I'll just highlight those so we can see all of our final answers in green. So it's a little bit different. If you had done a mole ratio, right, you would have gotten 4 moles if we start with 2 and double is produced. But you can see that it's slightly less than 4, which means some reactants left over and some of the product is missing than what should be there for a complete reaction. So whenever you see this double arrow, right, we have to evaluate concentrations using the equilibrium ice table method instead of stoichiometry mole ratios. Okay, but don't forget the mole ratios are still there, just takes into the account the percentage that actually forms versus what doesn't. Okay, and you'll have enough information to solve this in some way. So to follow up with that, if we want to represent that graphically, right, I'm going to do concentration over time, and we usually measure time in seconds. We talked about that in Unit 2. So we'll use some different colors here. To start off, concentration of hydrogen fluoride is 0, and then it increases and levels off at 3 moles per liter. Okay, if we label that as 3, we should be consistent. So 1, we'll call that 2. That means the initial concentration of hydrogen and fluorine was starting at 2, and it decreased to about 0.5. So it should end somewhere along there. Right? And we've got that evening out. Now I'll just use a funny pen here. We won't be able to overlap those well. That's why I just showed them separately. But this line technically represents the hydrogen and the fluorine gas separately, whereas this line represents the hydrofluoric acid or the hydrogen fluoride. Okay, so you can see that it levels off. That dashed line represents equilibrium. The concentrations don't change anymore. And notice how these don't touch 0 because there's always reactant left over in an equilibrium reaction. Okay, so this is an important example. Feel free to watch that and follow up with any questions if you need to. Right, we'll zoom in here and I'll do a slow scroll through it. But this is the basis of the entire unit, so spend some time with this. All right, so to wrap this up, we'll look at 3 scenarios. We'll call them A, B, and C. All right, so which one is at equilibrium and why? Feel free to pause. Okay, try these yourself. It's such an important tool to do. And if you've paused and you're coming back now, let's go through this. So the conditions for equilibrium were a closed system and no macroscopic change, meaning you can't see it, but it's there. Okay, so a sealed bottle of a carbonated drink, is it at equilibrium? Well, it's a closed system. That's good. And is there a change? Yes, what's happening is that the carbon dioxide gas is dissolving into the water, which is what you taste, and then when you take off the cap and you hear that, that's the gas being released, right? So there's no macroscopic change and there's a chemical process happening. So yes, this reaction is at equilibrium. A sheet of ice covering a lake at 0 degrees. So if we kind of scale out the lake, we show ice. It's at 0 degrees. Underneath, so from the ice below, yes, it's closed because the ice seals off the water below it. And because it's at 0 degrees, that tells us that the process occurring is that liquid water is exchanging into the solid state. So yes, this is also an equilibrium. So the information, again, we have to model it and identify what the process is that's happening, that's reversible, and if it is a closed system or not, which both are. Now the last one, a puddle of water evaporating. It is not a closed system, so it cannot be in equilibrium, and it's only a one-way arrow because liquid is turning into gas. There's nothing to state that the gas is turning back into a liquid, so no, that's not in equilibrium. All right, so hopefully you tried those yourselves or you rewatch that and understand the explanation for it, but we have to understand that equilibrium occurs under those conditions. Finally, do you agree with this statement? In a sealed jar of water at equilibrium, the quantity of water molecules in the liquid state equals the quantity of water molecules in the gas state or vapor. So pause, form an opinion, and when you come back, we should say to this answer, no. And the reason that it's no is that equilibrium does not mean the products and the reactants have equal concentrations. We saw that with our last example. So we can say the reactant concentration does not equal the product concentration. Always, it might be a coincidence, at equilibrium. Okay, it may, but it doesn't mean that it is. Okay, and that's the statement. That's the error with the statement there. If we added may equal, then yes, it would be okay. But as is, no. We can't say that that's a correct statement. All right, so that ends that. Be sure to reread chapter 7.1, follow up with those questions. And again, the ICE tables are key. Okay, every lesson we do in this unit will focus on applying these and how it looks at systems outside of complete stoichiometric ones.